Hey everyone, welcome back to The Explainer. Today, we're taking a pretty fascinating journey from the simple act of counting to uncovering the hidden visual codes of numbers. We honestly take counting for granted most of the time, but as we unpack the source material today, you'll see that there's this beautiful, structured logic hidden right in plain sight.
So let's dive into this by asking ourselves a really basic question. How do you actually count things in your day-to-day life? Think about it. When you look at a pile of coins or a crowd of people, are you painstakingly pointing at each individual thing, counting them one by one? Or does your brain kind of naturally just look for clusters and groups to speed up the whole process?
Here's our roadmap for today. First, we'll look at the art of grouping. Then, the power of pairs. Third, we'll define odd and even, move on to finding grid patterns, and wrap up by testing some math rules. Let's get right into it.
All right, part one, the art of grouping, seeing patterns in plain sight.
Let's start out in the real physical world, because math really always begins with observing the things right in front of us. It isn't just about symbols on a page, it's about making sense of our environment. The source specifically notes we should encourage counting using different ways of grouping and share that thinking. Basically, there's no single right way to count. But grouping? That's by far the most efficient trick our brains use to process quantities.
Take a look at Muniyama's stacks of cups here. You probably didn't look at this and start counting 1, 2, 3 starting from the very bottom left, right? No way. We instinctively count by vertical groups. We see stacks. Our brain registers a cluster of items as a single unit of measurement, which completely supercharges the speed and accuracy of our counting.
And you see this everywhere, whether it's going to pop up plucking exactly 5 coconuts from each tall tree, or analyzing the really satisfying orderly rows of coconut lottos and milk petas in a tray. Our brains are already doing math through visual grouping. We see a row of 4 sweets, another row of 4, and boom, we instantly know we have 8. We're literally multiplying without even realizing it.
Moving right along to Section 2, the power of pairs, featuring Shirley and Shiv's coin challenge.
Now check out the stark contrast here between Shirley's arrangements and Shiv's arrangements. Shirley was given 3 coins and 5 coins, and when she tried to group them into pairs, there was always this one coin left just kind of hanging out at the end. It breaks the pattern. But Shiv? He was given 4 coins, and he arranged them in perfect, unbroken pairs. 2 and 2. Absolute harmony.
So imagine handing Shiv 36 coins. Because of the nature of that specific number, we know for a fact those coins would pair up perfectly. 18 pairs side by side, 0 leftovers. And you know, that physical act of pairing, that's actually the exact gateway to our next big concept.
Which brings us to Section 3, defining odd and even, putting a name to the visual pattern.
So here's the crucial takeaway. The word even isn't just some random abstract math term you're forced to memorize. It literally represents the physical reality of objects perfectly matching up with a partner. Think about having an even number of guests at a dinner party. Everyone has someone sitting across from them, just like Shiv's 4 points.
Conversely, odd literally means exactly that, the odd one out. It means there is always going to be that one visual leftover that ruins the perfect symmetry. It doesn't matter how many pairs you try to make with Shirley's 3 or 5 coins, you'll always have a straggler. Always.
Now think about this awesome question from the text. Do you think all numbers in the times 2 table are even? Well, think about what multiplying by 2 actually does. It takes any amount and perfectly duplicates it. You are, quite literally, creating a pair for everything. So yeah, absolutely. The times 2 table is basically the ultimate factory for even numbers.
All right, Section 4, finding grid patterns. Let's zoom out from 1 to 100.
So when Shirley looks closely at the page numbers in her math book, she notices this really interesting even-odd pattern. And it turns out, when we take numbers and lay them out in a sequence like that, we uncover this incredible repeating structure. It's kind of like finding the hidden architectural blueprint of math.
Just look at this small piece of a number grid, starting from 1. If we label these based on our coin experiment earlier, we can clearly see this rhythmic alternating heartbeat. 1 is odd, 2 is even, 3 is odd, 4 is even. It's just a perfect, unending oscillation.
And the wild thing is, jump all the way down the page into the 50s and you'll see this rigid alternating pattern never actually breaks. 51 odd, 52 even, 53 odd. The columns remain perfectly stacked with either odds or evens. The behavior of these numbers is just incredibly predictable once you know how to look at the grid.
Which leads us to our final part, Section 5, testing the math rules. What happens between the numbers?
By staring at that grid, Shirley and Shiv managed to figure out two absolute laws of counting. First, the numbers immediately before and after an odd number, they are always even. And second, the numbers immediately before and after an even number are always odd. So if you know the status of just one single number, you instantly know the mathematical identity of its neighbors. Zero calculation required.
Okay, let's actually test this out with a simple step-by-step exercise. Let's take the digits 1 and 6. If we put them together to form the number 16, we know from our grid that it's even, it can be paired. But if we just swap those exact same digits to make 61, the entire nature of the number shifts. It instantly becomes odd.
And that brings us to this fantastic challenge. Choose any two digits and make two-digit numbers in such a way that the numbers are always even. Now, to engineer an even number like that, you have to be really strategic about which digit goes at the very end, because that final digit, that's the ultimate decider. If the last digit is an even number, like 2, 4, 6, or 8, then the entire number, no matter how massive it is, can be perfectly paired up, just like Shiv's coins.
All right, I'm going to leave you with this final provocative puzzle to chew on. Are there more even or odd numbers between 1 and 100? Knowing everything you now know about that endless, alternating heartbeat of pairs, the grid, and how every odd sits right between two evens, what's your answer? Really think about it. Anyway, thanks for joining me on this explainer. I'll catch you on the next one as we keep breaking down these fascinating hidden structures in the world around us.